The Poisson probability distribution. Another important discrete probability distribution is the Poisson distribution. The Poisson distribution is used to determine the probability of X successes in an interval of time or within a specific region. For example, the number of car accidents at a given intersection in a week, the number of customers at a bank in a given hour, or the number of chocolate chips in a Chip Ahoy cookie. So it could be within a specific interval of time or a specific region, like one single cookie. Or it could be a box of cereal. How many marshmallows are in a box of cereal? Let's look at the characteristics of the Poisson distribution. The number of successes that occur in any given time interval is independent of those that occur in other intervals. For example, a customer showing up in the morning does not affect a customer showing up at noon. The events are independent. 2. The probability of success is the same for any interval of equal length. The probability of a customer showing up within 30 minutes is the same throughout the entire day. The probability of X successes in a fixed time interval of length t is given by the following formula. P of x equals lambda t raised to the x times e raised to the negative lambda t divided by x factorial, where lambda equals the mean number of successes in an interval of length 1. E is the mathematical constant 2.7183, and this can be found on your calculator. X equals the number of successes in an interval of time t, and t is the length of the interval. To use this formula, we need to be given lambda, the mean number of successes, the mean, and the variance of the Poisson distribution are as follows. Mu equals lambda times t, and the variance is also equal to lambda times t. Thus, we can usually write the previous formula by replacing lambda t and lambda t with mu. We get the following formula. P of x equals mu to the x times e to the negative mu divided by x factorial. The previous formula can be simplified by replacing all of the lambda t's with mu into this equation. Let's try an example. A local gas station typically gets 0.2 customers per minute. What is the probability that 2 customers will arrive in the next 15 minutes? Notice that 0.2 customers per minute is given. This is my lambda. Lambda is 0.2 because that's the number of successes per 1 minute. Now t, the length of our interval, is going to be 15 minutes. And from here we could find mu. Mu is equal to lambda times t. And so all I need to do is multiply 0.2 times 15 and I will get my mu. And this is 3. And that means in that 15-minute interval, I expect 3 customers to show up at this gas station. Now let's look at the actual question. We want to know the probability of exactly 2 customers showing up. We want to find the probability of 2 customers showing up, so I want to find P of 2. We want to find the probability that exactly 2 customers show up, so we'll plug in the values into the formula here. Mu we know is 3, and x is 2. P of 2 equals 3 raised to the second times e raised to the negative 3. And we're going to divide that by 2 factorial. I'm going to enter 3 first. And in order to raise it to a power, we're going to enter the caret symbol here. Click caret. And we have 3 raised to the second power. To enter e, I'm going to press second, then the natural log, and it shows up e. We're going to raise e to the negative third power. So I need to make sure I press the correct negative. Don't use the subtraction symbol. Use the negative with the parentheses around it, and then press 3. So we now have e to the negative 3. I'm going to close off this parentheses, and then we will divide by 2 factorial. So we'll type in 2, and then we'll go back to PRB, and then select the factorial option. And this simplifies to 0.2240. So just type this entire expression into the calculator and you will get 0.2240. And if you need help on the calculator, feel free to send me an email and I'll show you how to perform these calculations on a calculator. Let's try another problem with a slightly different scenario. A local gas station typically gets 0.2 customers per minute. What is the probability that at least 2 customers will arrive in the next 15 minutes? This problem is slightly different because we use the phrase at least 2 customers, so it changes the problem completely. 0.2 customers per minute is still going to be our lambda because that's the average in 1 minute. So that's lambda. Our time interval is still the same, it's still 15 minutes. And therefore mu, which is equal to lambda times t, is still 0.2 times 15, or 3 customers in a 15-minute block. Now, this question is different because we want to find the probability that at least 2 customers will arrive in the next 15 minutes. So mu is equal to 3 and x is at least 2, so we're going to say greater than or equal to 2. I want to find the probability that x is greater than or equal to 2. This is equal to the probability of 2 customers showing up in the next 15 minutes, the probability of 3 customers showing up, the probability of 4 customers showing up in that 15-minute block, and so on. Now, this is impossible to do. We can't do the calculations forever, so we're going to have to find another way to do these calculations. I want you to recall that the area underneath this distribution has to add up to 1. The total area has to be equal to 1. But we know that if we have 0 customers showing up, plus 1, plus 2, plus 3, forever, and that sum should be equal to 1. Well, that means this is way too big because we don't have P of 0 or P of 1. So I'm going to actually subtract from 1 to calculate this probability. This is equivalent to 1 minus all of the things we don't want. I don't want P of 0 plus P of 1 in my calculations. So we'll subtract P of 0 plus P of 1. So this is now equal to 1 minus, for P of 0, we'll plug in x equal to 0 into the formula, and our mu is equal to 3. For P of 1, we'll plug in x equals 1, and our mu is equal to 3. So let's plug in the values into the formula. We have 3 raised to the 0, e raised to the negative 3, divided by 0 factorial, plus 3 raised to the 1, e to the negative 3, divided by 1 factorial. And then we'll simplify inside these brackets. And this simplifies to 0.0498 plus 0.1494. And this gives us a solution of 0.8008. This means we have an 80.08% chance that we will get at least 2 customers arriving in the next 15 minutes. Let's try another problem, but we'll change the scenarios again. A local gas station typically gets 0.2 customers per minute. What is the probability that 8 customers will arrive between 5:25 p.m. and 5:49 p.m.? Lambda is still going to be 0.2, and the time is given, but we'll have to do subtraction to calculate how many minutes there are between 5:25 and 5:49. If I do the subtraction, 49 minus 25 gives me a time interval of 24 minutes. Lambda times t is going to give us the mean, and so we have 0.2 times 24, which is 4.8. So in that 24-minute interval, we're expecting about 4.8 customers. Here, x is going to be exactly 8 because we want to know when 8 customers arrive. Again, mu is equal to 4.8, and x is going to be exactly 8. So we want to find p of 8, which is equal to 4.8 raised to the 8 times e raised to the negative 4.8 divided by 8 factorial. And if we plug this into a calculator, we get 0.0575. This means there is a 5.75% chance that 8 customers will arrive between 5:25 p.m. and 5:49 p.m. We can do all of these calculations with a handheld calculator, but we can also use technology to do these calculations. In the following problems, we will use technology to do all of the questions. Example, 1-800-FLY-FAST receives on average 2.3 calls per minute on their 1-800 number. Find the probability of the following. A, they receive exactly 5 phone calls in the next minute. B, fewer than 3 phone calls received in the next minute. In this question, we have 2.3 calls per minute. That is going to be lambda. Lambda is 2.3. In part A, they receive exactly 5 phone calls in the next minute. That's our x. We want x to be exactly 5. And t is 1 minute, so t is equal to 1. And so I want to find p of 5, and for this we'll go to our computer. We'll enter 2.3 for lambda and x equals 5. Let's change this to equals option, and that's our solution, 0.05378. 0.0538. There is about a 5.38% chance that we receive exactly 5 phone calls in the next minute. And that's for part A. For part B, in part B, we have lambda is equal to the same value. Lambda is still 2.3. but we want to find fewer than 3 phone calls received in the next minute. Fewer implies less than, so I want to find x less than 3, and this is in the next minute, so t is still equal to 1. So I want to find the probability that x is less than 3, so that's equal to p of 0 plus p of 1 plus p of 2, and I don't include 3 because we want it to be strictly less than 3. So I can do the calculations by hand by plugging these into the formula if I like, or we could do the entire thing on a computer, which I'm going to do now. I'm going to enter 2.3 for lambda. For x, if we were to enter 3, there is no option that says less than 3. There's only a less than or equal and a greater than or equal. There's no option that says less than 3. So we're going to have to do a compromise. I'm going to change this to 2 and put less than or equal, which means less than 3. Less than 3 is 0, 1, and 2. So we're going to use the less than or equal because that's equivalent to saying less than 3. I know, kind of confusing, but we're trying to make this class free for a lot of students, so we'll have to compromise by looking at free calculators online. And this gives me 0.5960. We have a 59.60% chance that fewer than 3 customers are going to call in the next minute. Let's try another example. A small town has 1.6 cars stolen on an average day. Find the probability that there are at least 2 cars stolen on a given day. We have the average per day is 1.6, so that's lambda, 1.6. We are looking for at least 2 cars stolen on a given day, so x is at least 2, greater than or equal to 2. And our time interval is just 1 because we're talking about a 1-day time period, so t is equal to 1. And so I'm looking for p of x greater than or equal to 2, which is equivalent to p of 2 plus p of 3 plus p of 4, and so on. Now, this is not possible to do, so if we were to do it by hand, I would have to subtract from 1, because I know starting from 0, 1, 2, 3, 4, and so on should add up to 1, but I don't want everything in front of p of 2, so we'll take away p of 0 plus p of 1. So this is the basic setup for those that wish to do this problem by hand. But I'm going to go on to the computer and calculate this Poisson distribution. In this problem, we have lambda is equal to 1.6 and x is 2, but we want to select the greater than or equal option because we're looking for at least 2 cars stolen on a given day, and we get 0.4750. And this is equal to 0.4751. There's a 47.51% chance that at least 2 cars is going to be stolen in a given day. That sounds pretty crazy to me. This is pretty crazy. So many cars stolen. Example, the mean number of bike crashes at USC is 2.1 crashes per day. Find the probability that USC will get 6 bicycle crashes over any given 2-day period. Pause the video and try the problem on your own. Lambda equals 2.1 and x is going to be exactly equal to 6 because we want to have 6 bicycle crashes, and t will be equal to 2. Mu is equal to lambda t, and so this is equivalent to 2.1 times 2, and we get 4.2 from that. If we wanted to do the calculations by hand, we would look for P of 6, which is equal to 4.2 raised to the 6 e raised to the negative 4.2 divided by 6 factorial. So you can type this in a calculator, but I'm going to go to our computer to do the calculations. We enter 4.2 for lambda. I know lambda is not equal to 4.2. The calculator is different in that this is actually supposed to be the mean. X is equal to 6. And I want to select the equal option because we want to have it exactly equal to 6. 0.1143. So there's about 11.43% chance that we're going to have exactly 6 bicycle crashes. We have about 11.43% chance that we're going to get exactly 6 bicycle crashes in a 2-day period.